In section 2.8, we will establish an inequality called Farnell's inequality, which will be used over and over again in this course. Before we establish Farnell's inequality, we first prove a very useful theorem. This theorem says that for any random variable x, the entropy of x is upper bounded by the log of the size of the alphabet. This upper bound is tight if and only if x is distributed uniformly on the alphabet. We now prove theorem 2.43. Let U be the uniform distribution on the alphabet x. That is, Ux is equal to 1 over the size of the alphabet for all x in the alphabet. Then, log of the size of the alphabet minus entropy of x can be written as follows. First, we write log of the size of the alphabet as minus summation x in the support times px times log 1 over the size of the alphabet. This is because summation x in the support px is equal to 1 and log of the size of the alphabet is equal to minus log of 1 over the size of the alphabet. We also write minus entropy of x as summation x in the support of x, px times log px. Now 1 over the size of the alphabet is equal to u of x. By combining minus log ux and log px, we obtain log px over ux. And this is recognized as the divergence between p and u, which by the divergence inequality is always greater than or equal to 0. And this proves the inequality in 1. This upper bound on the entropy of x is tight if and only if p is equal to u, that is, x is uniformly distributed on the alphabet x. Theorem 2.43 has the following implications. First, for a random variable x, if the alphabet is finite, then we have entropy of x less than or equal to the log of the size of the alphabet, which is less than infinity. That is, entropy of x is finite. Second, the entropy of a random variable may take any non-negative real value. That is, for any a greater than or equal to 0, we can find a random variable x such that the entropy of x is equal to a. For details, please see Corollary 2.44 in the textbook. There is something which is not implied by Theorem 2.43. For a random variable x, if the alphabet is infinite, then the entropy of x can either be finite or infinite. Next, we are going to give an example that a random variable x has a countable alphabet, but the entropy is finite. Let x be a random variable such that the probability of x equals I is equal to 2 to the power minus I, for I equals 1, 2, so on and so forth. Then, the entropy of x in bits is equal to minus summation I from 1 up to infinity, 2 to the power minus I log 2 to the power minus I, where 2 to the power minus I is the probability that x is equal to I. Now log 2 to the power minus I is equal to minus I, and so we have summation I from 1 up to infinity, I times 2 to the power minus I. This is the expectation of a truncated geometric distribution, which is equal to 2. Therefore, the entropy of X is finite. Next, we give an example of a random variable whose alphabet is countably infinite, but the entropy is infinite. Let y be a random variable which takes values in a subset of pairs of integers ij, I from 1 to infinity, and j from 1 to 2 to the power 2 to the power I divided by 2 to the power I. Note that the range of j depends on the value of I. The probability that y is equal to ij is equal to 2 to the power minus 2 to the power I. Note that the probability that y is equal to ij depends only on the value of I, but not the value of j. First, we check that this is a proper probability distribution. To do this, we sum probability y equals ij for all I and all j. Now the probability that y is equal to ij is equal to 2 to the power minus 2 to the power I. The number of terms in summation j is equal to 2 to the power 2 to the power I divided by 2 to the power I. So we multiply by this factor 2 to the power 2 to the power I divided by 2 to the power I. Now 2 to the power minus 2 to the power I cancels with 2 to the power 2 to the power I, and what we are left is summation I from 1 up to infinity, 1 over 2 to the power I, which is equal to 1. Then we evaluate the entropy of y in bits. This is equal to minus summation I, summation j, 2 to the power minus 2 to the power I, log 2 to the power minus 2 to the power I. Now log 2 to the power minus 2 to the power I is equal to minus 2 to the power I. Now in 2 to the power minus 2 to the power I times minus 2 to the power I, the minus sign cancels with the minus sign here. So we get 2 to the power minus 2 to the power I times 2 to the power I. The number of terms in summation j is equal to 2 to the power 2 to the power I divided by 2 to the power I. So we multiply this factor. And so 2 to the power 2 to the power I cancels with 2 to the power minus 2 to the power I. And 2 to the power I cancels with 2 to the power I. Therefore, we have summation I from 1 up to infinity, the constant 1, which does not converge. This means that the entropy of y is equal to infinity. Now we discuss Farnow's inequality. Let x and x hat be random variables taking values in the same alphabet script x. Then the conditional entropy of x given x hat is upper bounded by hb of pe plus pe times log of the size of the alphabet minus 1, where pe, called the error probability, is equal to the probability that x is not equal to x hat. That is, x hat is a wrong estimate on x. And hb is the binary entropy function. Here's the intuition for Farnow's inequality. Suppose x hat is an estimate on x. If the error probability pe is small, then the conditional entropy of x given x hat should also be small, because this conditional entropy measures the uncertainty about x when x hat is given. This intuition is captured by Farnow's inequality because of the following. For a fixed alphabet size, this logarithm is a constant. And for small pe, hb of pe is very close to 0, and pe plus the logarithm is also close to 0. Therefore, this upper bound is a very small quantity, and therefore the entropy of x given x hat is also a very small quantity. We now prove Farnell's inequality. First, define a random variable y which is equal to 0 if x is equal to x hat, and it is equal to 1 if x is not equal to x hat. Y is an indicator of the error event x not equal to x hat. Then, the probability that y is equal to 1 is equal to PE, and the entropy of y is equal to HB of PE. Since y is a function of x and x hat, entropy of y given x and x hat is equal to 0. Then, hx given x hat is equal to hx given x hat plus hy given x and x hat. This is equal to entropy of x and y given x hat. To see this, we note that entropy of x and y given x hat can be expanded as entropy of x given x hat plus entropy of y given x hat. Next, we expand entropy of x and y given x hat into entropy of y given x hat plus entropy of x given x hat and y. Now entropy of y given x hat is upper bounded by entropy of y. For entropy of x given x hat and y, we now expand it by conditioning on the values taken by x hat and y. To do this, we first sum over all x hat in script x, and then consider probability x hat equals small x hat and y equals 0 times the entropy of x given x hat equals small x hat and y equals 0, plus the probability that x hat equals small x hat and y equals 1 times the entropy of x given x hat equals small x hat and y equals 1. For the first case, that is, x hat is equal to small x hat and y is equal to 0, x must take the value small x hat, because there is no error. In other words, x is conditionally deterministic given x hat is equal to small x hat and y is equal to 0. Therefore, the entropy of x given x hat equals small x hat and y equals 0 is equal to 0. As such, the two terms for the first case go away. For the second case, x hat is equal to small x hat and y is equal to 1, that is, the estimate is incorrect, x must take a value in the set x in script x such that x is not equal to small x hat, which contains the alphabet size minus 1 elements. By theorem 2.43, we have entropy of x given x hat equals small x hat and y is equal to 1 is less than or equal to log of the size of the alphabet minus 1, where this upper bound does not depend on the value of small x hat. Hence, following step 3, entropy of x given x hat is upper bounded by this expression, where HBPE is equal to entropy of y log the size of the alphabet minus 1 is an upper bound on entropy of x given x hat and y is equal to 1. Now this summation, which is the summation over all x hat, probability x hat equals small x hat and y is equal to 1, is simply the probability that y is equal to 1, and this is equal to PE, the probability of error. This completes the proof of Farnell's inequality. We have just proved Farnell's inequality. Corollary 2.48 is a simplification of Farnell's inequality, which says that entropy of x given x hat is less than 1 plus PE times the log of the size of the alphabet. This is obtained by further upper bounding HBPE by 1 and log of the size of the alphabet minus 1 by log of the size of the alphabet. Here are a couple of remarks. First, for finite alphabet, if PE tends to 0, then the entropy of x given x hat also tends to 0. However, this may not hold for countably infinite alphabet. In other words, for a small PE, entropy of x given x hat may be large. Please see example 2.49 in the textbook.